the other algorithm, the bigger algorithm, we have to kind of do some exercises ourselves just so that we know, systematically speaking, how do we find whether a prime number, how do we find a prime factor given a specific number? How do we do that? Now, you can always start with numbers that you're familiar with, like 48. But remember what I said? We can use a lot of rules of thumb or heuristics that is not worthwhile to program in a computer. We know 48 is divisible by 2 right away because it ends with an even number. We know 33 is divisible by 3 because 3 plus 3 is 6, and 6 is divisible by 3. So we have all these little rules of thumb, including 25. We know it has to be divisible by 5 because it ends with 0 or 5 as a decimal number. And someone can say, yes, but we can actually write that code into a computer and use the same heuristics as a human can. That is true. Okay? How does a computer represent numbers internally? Does it use decimal numbers? No. What kind of number does it use? It uses base 2, binary numbers. Very good. So if you look at binary numbers, we don't have the same tricks anymore. The only trick you can use in binary numbers is to tell whether a number is divisible by 2, 4, 8, 16, and so on. Those are easy to check, but everything else is not as easy. Well, the tech, you can always convert a binary number into decimal, and then we can extract the least significant digit and match it with some of those numbers. Trust me, that's not worth the time, okay? Because base conversion is kind of slow to begin with, so the time that a program spends to do base conversion is already taking time away that it could have spent on a simpler and more efficient algorithm. Okay. Besides, those tricks only work on smaller numbers. It does not work on numbers like this. So when you look at a number like this, you have to resort to a much more systematic way of solving this problem. Now we know that out of heuristics, 2, 3, 5 are definitely out. But we cannot just visually look at this number and know that 7 is not a prime factor of 5, 6, 7, 1. So how do you know that 7 is not a prime factor of this number? Well, you actually have to try to divide it, don't you? So when we try to divide this number by 7, we have 8 here, 1 here, 0, with a remainder of 1. Okay, now which part tells me that this number is not divisible by 7? Is it a quotient or is it a remainder? A remainder. Very good. So it seems like the remainder is kind of important in this sort of calculations. Okay, so we know 2 is not a prime factor, 3 is not a prime factor, 5 is not a prime factor, 7 is not a prime factor, and someone who is really smart will say, let's try 11. And basically bypassing 8, 9, and 10. Why? Because those are not prime numbers. Now, let me ask you another question. If I try, let's say I'm really dumb, not very bright, and I just say, let's try 8, because if 7 is not a prime factor, we'll try 8. It's not a very smart thing to do because it is going to use up time, but is it wrong to do it? It is not wrong to do it. In other words, it is not possible for me to try to divide this number by 8 and yet have a remainder of 0. Is that making any sense? No?
Can you repeat that?
Okay. It is not smart to try to divide 5, 6, 7, 1 by 8 because, it's not a prime number to begin with. But it is also not wrong to try it because it won't give me a wrong answer. It will not mistake 8 as a factor of 5, 6, 7, 1. But why is that the case? It's because 8 is a composite number, composing only of numbers that we have tried already. And since those numbers all yielded non-zero remainders, that means 8 as a composite number is also guaranteed not to give me a 0 as a remainder. So in this case, you can say that it's 7, 0, that will be 8, with a remainder of 7. Okay? In other words, if you want an algorithm that is simplistic, that's easy to understand and easier to write, if it is too much trouble to skip composite numbers, go ahead and test them anyway. Okay? Your program will take a little bit longer to execute because you will be testing numbers that cannot possibly be prime factors, but at the same time, the program will be easier to write because you don't need to know all the prime numbers ahead of time, and it is just easier as a first revision. We can deal with optimizations later. So for the same reason, you can also try to divide it by 9. We know it is a waste of time, but at the same time, it is not an error. It will not give you the wrong result. So we keep doing this, until when? Until we actually find a prime factor. Now, what do you think this number is prime? You guys know how to search for prime numbers if you want to? I would just use Google prime and then just punch in that number. Because if it were prime, then some maniac would have listed all the prime numbers up to some gazillion places. All right. Well, I guess it is. Oh, maybe not. Triangular number. So 5, 6, 7, 1. Wait, why is it? Search. Oh, it's called a triangular number. Doesn't say whether it's prime or not. Hmm?
Is 5,
Mm-hmm.
6, 7, 1
Oh.
instead of 5, 6, 7, 1.
And end with a question mark just to be sure. Not yet. How about prime number list? List of prime numbers. And 5, 6, 7, 1 is not on it. So, it is not. It's a non-prime number. Great. Well, if your homework assignment is to find the prime, find the prime factor of 5, 6, 7, 1, what are you going to do? Well, unfortunately, you have to keep doing this until you find it. So that makes it a not very good example, but that's fine because all we want to do right now is to find out a systematic way of finding a prime factor given a number n. Okay, so we can switch back to the text editor and say, let's go from revision 1 again. So this time our objective is to find a prime factor given the number. We don't need to find all the prime factors, just one. Give me one and we're good. Okay? So the problem, if I want to describe the problem, given a number n that is greater than 1, okay, let's make it an integer to be more specific. Find a prime factor f. There we go. First of all, is it repetitive? If you just think about 5, 6, 7, 1, was that approach repetitive? How we try to find a prime factor? Well, it was repetitive. We try 2, and then we try 3. We can try 4, even though it's not very smart, but we can try it. Try 4, 5, 6, 7, and so on. So we know that it is involving a loop of some kind. And when do we exit the loop? When do we get out of that loop? We start with 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc., etc. When do we stop?
When we get to the number 5, 6, 7, 1.
When we find a factor. Well, we won't get to 5, 6, 7, 1 because it is non-prime. So we know that we have to stop kind of way before that. Given the number is a composite number, we are guaranteed to stop at the most up to the square root of that number. Okay? So we basically exit when we find a prime factor f of n. Okay? Well, we'll call it one revision because we have already identified two important things again. One, it is a loop, and two, we get out once we confirm that f is a prime factor of n. Okay. Revision 2. Revision 2 is to say, can we say this a little bit better? Can I use more programmatic or mathematical notations? So the result of that is we can say something like this. We can say when n mod f equals to 0. Okay. The mod operator is kind of like a division operator, except we don't pay any attention to the quotient. This gives you the remainder of the division. So when you say n mod f, the result is the remainder of n divided by f instead of the usual quotient of the division. Okay. And mod stands for modulus. There's an entire branch of mathematics that deals with modulo arithmetics. Modulo arithmetics is basically something that you guys will eventually all deal with. Remember what I said about the number line is not exactly a number line in computer programming. Instead, it is more like a wheel. Every time you have a number system that is a wheel, it becomes a modulo system. Okay, because when you add 1 to the largest number that you can represent, it becomes 0 again. Okay, and that's modulus arithmetic or modulo arithmetic. Okay. So all we have to do is to remember that mod is the remainder. It returns the remainder of a division. All right, we'll look at revision 3. We look at this code here, and we say if initially f is not a factor of n, we have to do something about either n or f so that this condition will eventually be true. Because if I don't do anything to n and I don't do anything to f, and initially n mod f is non-zero, then the loop will never exit. So that tells me that in the loop, we have to do something about one of these two at least. Do we want to do anything about n? In other words, if someone tells me, Tech, why don't you try to find a prime factor of 16? And my answer is, I know 2 is a prime number. Well, that's not a good example. Let's try something else. Someone tells me n equals to 15, okay? And that person tells me, Tech, why don't you find a prime factor of 15? And my answer is, I don't know. 3 is a prime number. 2 is a prime number. I just pick something that has nothing to do with n. That's not good. So that means I don't want to modify n because I want to keep using n mod something as the condition to get out of the loop. So that means the only thing I can change is f. Okay? Now, when you try different factors of n, you can obviously try kind of in random. In other words, we don't have to start with 2, we can start with 11. And then we move to 2, and then we go to 7, then we move to 5, then we move to 19, and so on. But is there any reason to do that? No? So it makes more sense that we'll just be testing sequential numbers. If you're testing sequential numbers, what are we going to do to f in the loop to make it go like, well, since 2 is not a prime factor, we move on to 3. How do we move from 2 to 3? We add 1 to f. Okay, so we just f gets, wrong place. F gets f plus 1. So this is almost it already. This is almost it. Because we have identified several really, really important things. We have identified this is a loop. We get out when n mod f does equal to 0. And when that is not true, when n mod f is not true, we keep moving on to the next available number and try again. If it doesn't work, try again, add 1 to it, try again, and so on. So the question now is, what do we start off with? In other words, what would be the first number to try?